The area of a rectangle is 48 square feet and its perimeter is 32 feet. Find the length and the width. We have answered questions like this in the past using systems of equations. We have two constraints that are required in order to solve a problem, and you solve the two of them simultaneously. We can write a quadratic model that allows us to engage in that same kind of thinking. So we're going to start with, unlike our last example, we're going to start with two different variables, x and y, as representations of the length and the width. We know that the area of the rectangle is 48, so x times y must be 48. And we know that the perimeter of the rectangle is 32, so 2x plus 2y must be 32. The quadratic model comes into play when we use the substitution method on this bottom equation and substitute it into the top equation. Solving the bottom equation for x, we get that x is equal to 16 minus y. We subtract the 2y over, then we divide by the 2. We get x is equal to 16 minus y, which means we can rewrite the first equation in one variable as 16 minus y times y is equal to 48. And you're already starting to see where the quadratic model might come into play. Distributing the left-hand side, we get 16y minus y squared is equal to 48. Solving this for solving this for 0, I move all the terms over to the right-hand side. We get the polynomial y squared minus 16y plus 48. Factoring that, we get two solutions, y is equal to 4 and y is equal to 12. Now, the unique thing about this answer is that it would seem that both of these are good answers. Like, both of these could be values for x and for y, and that's true. You could make y equal to 4 or make y equal to 12. The neat thing about this example is when y is equal to 4, then if you look right here, x would have to be 12, and when y is equal to 12, then x would have to be 4. So when you solve it in a question like this, you're actually solving you're solving it for both of the variables at the same time. Because of their product relationship right here in the area, you actually found both of the potential values at the same time, which is a neat consequence. Let's look at a slightly different example. And if you read through this example, it's going to feel a lot like the last one, where you have an area and you have a defined perimeter. But the difference for this one is that you're going to have a maximum area that you are going to look to attain. And that's where our function writing and our graphing and our thinking about the vertices and axis of symmetry is going to come into play. So we have a river going this way, and we are going to fence in a rectangular space against that river. We know that both of these sides, as this is a rectangle, need to be the same. And we know that we have 196 total feet of fencing. 196 minus 2x is left over for the long side of the rectangle. And we want to maximize the area that is taken up by this rectangle. So we're going to write ourselves an area function. The area function as a function of this length x. We could have done it on this side. There's a way to do it on this side, but it's a lot easier to make the two sides that have to be the same, both x, than it is to make the one side that's different equal to x. So we have the area is x times 196 minus 2x, and the area is 196x minus 2x squared. And our area function, rearranging the terms a little bit, so we're in standard form, negative 2x squared plus 196x. There's our standard form. This is the function that we are looking to maximize. We know that the graph of this function, and we're not even going to look at the graph. We want to start to be able to visualize it. We know that this graph is going to be a parabola that opens downward. Thank you to the 2 being negative. We know that this graph is going to start at the y, or the origin, because there's no plus c at the end of the function. So a rough sketch, we know we're going to start here. We know we're going to be a bowl that opens down. And we know that we're going to have a vertex somewhere in this space. and that vertex is going to be halfway between the two x-intercepts. So you could determine the other x-intercept if you really wanted to. We could factor and solve, or we could just jump right to that vertex that we know is at the top. So let's use our vertex formula, negative b over 2a. Negative b is negative 196. 2 times negative 2 is negative 4. Multiplying the denominator and then dividing, we get that the x-intercept is at 49. Or I'm sorry, the vertex is at 49. So the maximum length, or I shouldn't say the maximum length, the maximum area is obtained by making this length 49 and this length 49. Once we have that, we can go back to the original area function, and we can evaluate that original area function at x is equal to 49. And if you're careful with your arithmetic, you should get that the maximum area that's attainable is 4,802 square feet. So looking at these last two examples that we just completed, we had a defined area and a defined perimeter. In that case, there was one specific, well, I shouldn't say one. There was two combinations that worked, either 4 and 12 or 12 and 4. In this example, we have an infinite number of possibilities, an infinite number of ways that we could use that 196 feet of fencing. But because we did not have a specific area in mind, we were able to instead write the function so that it had all of the different possibilities all available to us, and then we maximize that function. Knowing what we know about the graph of quadratic functions, knowing what we know about how to identify the vertex, we found our highest point, we found our turning point, we found that maximum, and then we use that to find the maximum area.